So hello viewers, welcome to the video series of Layer-3 on networking. So in this series we have already finished with the static routing. We have seen the theory part of the static routing, then we have simulated the static routing in Cisco packet pressure, and also we have seen that how we can simulate static routing in the NS3. If you are new to this channel and not watched all of those videos, so I'll probably link down all of those videos into the description box. You can check that out and follow along with this tutorial. And in this video, we'll see and we'll learn RIP protocol. So without wasting much time, let's get started. So the content of this playlist or the video series on the RIP protocol, so that content follows like this. So first we'll introduce the RIP obviously, then we'll have a brief discussion on the distance vector, then RIP history followed by the RIP protocol, some of the theory part, then one by one we'll simulate the RIP inside Cisco packet tracer and also in the NS3. So without wasting much time, let's get started. So the first thing, introduction covers this. So I would like to give you just an overview of the layer 3 and which is routing layer, as you might all know. So routing is done like there are basically two ways of doing a routing. So first one is static routing that we have seen, and as I said, I'll link down all of those videos that how we can simulate static routing, the theory portion and all of those videos. So go check that out if you are new to this channel. The second part is dynamic routing. So now we are starting with the dynamic routing, and RIP falls under this where is this? Okay, here, distance vector. So RIP protocol falls under the dynamic routing protocol types. Okay, and dynamic routing, and also there are like two parts inside the dynamic routing. So there are two ways we can achieve dynamic routing, which is IGP and EGP. And the sense of this both ways of doing dynamic routing, it itself in this word only. So the word IGP stands for Interior Gateway Protocol. So those protocols are the only protocols which is used inside the AS, and AS is like an autonomous system, and it can be referred as any organization or any network. Basically, when I am running an organization, so I'll probably buy an AS number, autonomous system number, to get connected over the internet. So that's inside an IS. So internally, whatever the devices I have, so for routing all of those devices, because all of those devices will also have some IPs, right? So to have a connectivity between those devices, I'll run IGP. So these are the all protocols that will be used in for inside the AS, that is known as IGP. And EGP is basically the protocol which can be used to route your network all over the internet. So that's nothing but between AS. So between your organization and let's say your friend has some organization, has it's he has his own network, he has his own organization. So how will you advertise your network over the internet to your friend? So to achieve that routing, we'll use EGP. That is nothing but exterior gateway protocol. So BGP can be used inside EGP and IGP as well. So the BGP, that is the flavor of BGP that can be used between AS or in EGP, that's eBGP. So basically exterior border gateway protocol, and which can be used inside IGP, that is nothing but IBGP, that is interior border gateway protocol. Now again, there are two ways we can achieve IGP. So not the two ways, because it cannot be distinguished the way, but it is like what are the algorithms that are being run by the protocol. So this OSPF and ISIS, basically they run link state the protocol. not the protocol, but the algorithm to have to choose the best path. So that's why inside IGP, the link state algorithm, these are the protocols that uses link state algorithms, so SPF and ISIS, and these are the protocols that uses distance vector. Okay, so RIP uses distance vector. It falls under IGP because it can only be used inside AS, and in IGP falls under these dynamic routing protocols. So this is nothing but an introduction of RIP. Okay, so distance vector algorithm. So the deep understanding of distance vector algorithm that you might have got inside the subject called DSA if you are a computer engineer, because that stands for data structure and algorithms, and you have got this overview of distance vector. So basically, you might have heard these terms like Dijkstra's algorithm or Bellman-Ford algorithm. So these two algorithms uses distance vector. So let's explain. I'll explain the basic working of the distance vector algorithm. I'll not go into the brief, but just for the understanding, you should know at least this much, that whatever I'm going to tell you right now. So let's say these are the three devices or three routers X, Y, and Z, and these are the cost of this path. Let's say 1, 2, and 5, and this router will have something called this kind of matrix. So let's say for this router X, it will have this matrix, and this matrix basically represents, let's say if you are standing at X and you want to go to X, so you will cost 0, or because you are standing at the destination only. And but let's say you are standing at X and you want to go to Y, so the cost for going Y is nothing but 1. And now you are standing at X and you want to go to Z, the cost is 5. So this is the initial whatever, let's say, matrix or the cost matrix for the devices. So that's let's say you can also call it this cost as in distance. So let's say after routing table exchange, so we are running, so let's say some dynamic routing protocol, and this router exchange is the backend. So let's say the first exchange that is happening is between X and Z. So router X and router Z, they both exchange the routing table. So X advertises its own routing table to Z, and Z also advertised his or its own routing table to X. Okay, now how the cost is being calculated is like this. So for, let's say, the distance that you the or not the distance, the cost that is that requires to travel from X to Z, it is equals to the cost required travel from X to Y plus the cost required to travel from Y to Z. So this is the formula that is being used, and that's how after the routing table exchange, the X comes to know that if I want to go to Z, this is the shortest path. So because it takes the only cost 3, but this path is taking cost 5. So I should update my path, and this was the older let's say routing table, and this is the new routing table. Now it also has the Z entry. So for this router Z, these are the entries, and these are the updated values. So whatever these are in the red, and D, as I said, D of A comma B, it is nothing but the distance or the cost travel from A to B. So this is how distance vector is running in the background. And let's say there is a second routing table exchange between X and Y, and now these are the routing tables, and this is the key function that is being run, and these are the costs. So that's how the distance vector is running behind this dynamic routing protocol, and that's how the shortest path will be calculated. So as I said, the distance is nothing but a matrix that can be anything in this algorithm. So this distance vector algorithm, the distance meaning of the distance is nothing but a matrix. So let's get to know about some RIP history. So the first RIP version 1 was published as a part of RFC 1058, but this RFC was not legally not legally, but it was not a legacy. The reason why it was not a legacy because it was not published, uh, like it was published before the IETF was formed. So it holds no standards and no formatting. But the core parts of the table of contents of this RFC were like this. And the whole idea of RIP version 1 was to broadcast the updates, and it was not supporting the authentication, as well as it was only built for the classical routing only. Now, RIP-NG or RIP-ING that was published as a part of RFC 2080, and it included the support for the IPv6 in the RIP. So this was the RFC for RIP with the support of IPv6. And now this is the RIP version 2 that was published as a part of RFC 2453, and this is the latest RIP version or the latest RFC for the RIP, and it included the multicast. The routing updates were like not now broadcasted, it was multicasted at 224.0.0.9. So this was the reserved multicast address for the RIP packets, and it supports, or it also includes support for the authentication, and it has the classless routing support. So now let's get to know about some RIP protocol basics. And what I mean by basics is we'll understand the packet structure or the packet format for the RIP. So the basics of RIP working is like it works on the blind multicast because there is no sense of neighborshipping or neighborship establishment in RIP. So it doesn't maintain the record of the neighbors. It just blindly multicast and ask for the routes or send the routes. So as I said, it has only two packet types defined, namely request and reply. So in request, it will basically request for the subnets or network, and it will in the reply it will reply for this particular request that was made by some other router. And it will also be this kind of multicast packet only. And the packet format for both of this type is almost the same. So the packet formation is something like this. So there will be Ethernet header, IP header, followed by the UDP header, and this UDP header includes the source port and destination port 520, which is nothing but the RIP service defined, or this is the reserved port for the RIP. Then UDP header will be followed by this RIP packet message, and the minimum size for this packet message is 24 bytes, and it can be up to 520 bytes. And how it is so the first RIP header is 4 bytes, then there will be some route entries, and per route entry will be 20 bytes in the size, and it can hold maximum up to 25. So this particular section will be the minimum of 20 to maximum of 500 bytes. So combining both of this, it ranges the minimum of 20 plus 4 as 24 bytes up to 500 plus 4. Okay, so it should be 24 to 504 bytes. Okay, sorry, this is a mistake. So the packet formation happens like this. Now this is the RIP message format. So this first 32 bytes is nothing but the RIP header, and RIP header is followed by route entries. There will be multiple, this many fields. It can be repetitive, depends on the how many route entries that are being advertised, and it can be maximum up to 25 entries per RIP message. Okay. So now let's get to know about some RIP header fields. So the first header field is command, and this command is nothing but what is the message format. So the request and response or reply that we have seen earlier, right? So if it is 1, that means it is request message, and if it's 2, that means it's a response message. So this is defined under the RFC 2453 section 3.6, and these are the types. Okay, so this is the particular cutout section that I have take from the RFC, so you can follow or watch or go for this RFC 2453. Now there is this version. So the version indicates what is the RIP version that is being running. So basically it's 2 for RIPv2. Now this address family. So address family. So when the router entries are being sent, it should clarify what is the address family. So basically for the IPv4 networks, so mostly it will be used for IPv6 only, and for IPv6 the address family identifier is 2. So route tag. So route tag is defined inside RFC 2453 section 4.2, and that basically nothing but the, let's say, it is an identifier for whatever the routes are being advertised. It is like advertised purely as a part of RIP, or those are like external route, like maybe it may be learned by some other protocol, and those protocols the routes from learned via those protocols are advertised using this RIP. So that route tag signifies the difference between those routes. Now this is a metric. So in the route entry, per route entry there will be a metric, and the metric value can be used to signify the cost of the particular to reach, like what is the cost to reach this IP network that is being advertised. And the value 16 is the max value that is defined inside the RIP, and it is used, the 16 is only used when the routes are being withdrawn, or whether they are asking for the routes. So for per route, if I want to ask what is next hop, then the value metric value 16 signifies that I am asking for that value. And also it can be distinguished from this command, the whatever this value of the command is here. So if it's a reply, that means I am not asking for it, I am withdrawing the route. And if it's a request, so that 16 value of the metric signifies that I am asking the value. So that's it for this video. Hopefully you have got the idea about RIP and all of the packet format, the basics of RIP and the distance vector algorithm. So that's it for this video. Hope you have got the idea about RIP. We'll meet in the next video and we'll see about how we can simulate RIP inside CPT and NS3. So hope to see you in the next video. Till then, keep learning and keep exploring.